Welcome you all to this FDP lecture, Faculty Development Program lecture series. First of all, I give my sincere thanks to Dr. Hussain, who organized this FDP Faculty Development Program. I am also grateful to him as he invited me to deliver a lecture in this faculty development program. The topic of my research interest, the topic of this invited lecture is the nanoparticles incorporated thin films and its sensing applications. And the thin films that we are working at present, these are the thin films fabricated by Langmuir-Blodgett technique, LB technique, and layer by layer LBL self-assembled technique. These two techniques that I will discuss here, and also how the properties of the thin films are modified when nanoparticles, namely the nano clay platelets, are incorporated into these thin films, and they are changing in properties can be applied for them to act as sensing devices. Here also I will discuss some basics idea or basic informations about nanoparticles, and then how these thin films are prepared and how the nanoparticles incorporated thin films are prepared, and then I will discuss in a lucid manner how these films can be applied in to act as sensing devices. I am Dept Bhattacharjee from the Thin Film and Nanoscience Research Laboratory, Department of Physics, Tripura University. And this Thin Film and Nanoscience Research Laboratory, this laboratory has the following members: the group members, faculty members involved, myself, Dept Bhattacharjee, and Dr. Soyad Arshad Hussain, and he is the associate professor, of course, and he is the organizer of this faculty development program. And at present, the scholars, Dr. Mitu Shah, and she is the CSRA scholar, and others are working for their PhD degree. Nilima is a part-time research scholar, and she is working as assistant professor in MBB College. And others are Sudeep, Surojit, Ripa, Ritunovo. They are the research scholars, and these research scholars are either working under my supervision. Actually, under my supervision, Mitu and there are Mitu and Nilima. They are working at present, and under the supervision of Dr. S. A. Hussain, Sudeep, Surojit, Ripa, and Ritunova, they are working. And already scholars awarded PhD degree from the Thin Film and Nanoscience Laboratory. They are Drs. Povitro, Subroto, Surojit, Nurul, Dhananjoy, Shantanu, Dibbendu, Joyashree, Arshad, Ashish, Shekhar, Shoma, Mitu, Chandan, Bapi, Joba, Pintu. And some of them are awarded under my supervision, and some others are awarded working under the supervision of Dr. S. A. Hussain. And Povitro, Dr. Povitro Kumar Pal, he is working as associate professor in the Department of Physics, Jadavpur University. Dr. S. A. Hussain, he is working as associate professor in the Department of Physics of this university, Tripura University, and also some other scholars, namely Subroto, Dhananjoy, Shantanu, Shoma, Chandan, Shekhar also. and they are working in different government colleges in Tripura, and others are also working in different places. Now, these are some brief introductions about our research laboratory and our group members. And now, the broad subject area in which we are working. Of course, we are working in the Department of Physics, and all of us are physics students, but and physics students and researchers in physics, but actually all of us are working in the broad subject area of material science. And this material science, it is an interdisciplinary area. And large number of subjects, namely physics, chemistry, mathematics, and then various technological important subjects like electronics, electrical, mechanical, computers, communication engineering, then biology, biotechnology, biophysics, biochemistry, and also nanoscience, nanotechnology, even medical science, and also even economics and sociology. Some of the researchers, they are working on various aspects of material science. Therefore, actually, this material science, it includes a large number of subjects, and it is an interdisciplinary area. And this material science, what is material science? That is, it deals with the materials and the processing of the materials. How the property of a material can be improved by changing its structure, and also by doping some other materials to a particular materials, how their structures can be influenced and how their properties, physical properties and chemical properties can be modified. These are the main topics of research interest in the material science. And using these modified properties of different types of materials, these materials have vast applications in various technological fields, namely namely electronics, electrical, mechanical, even in various biological fields. And these properties of interest of different materials, and these properties can be mechanical, electrical, magnetic, optical, antibacterial, even in biological science, it has a vast applications to develop some materials which has which have antibacterial properties, and also other materials can be developed highly insulating properties, and so on. And the applications involved that electronics, communication, medicine, transportation, manufacturing, recreation, energy, and the environment. And this material science is the oldest science in this world. It's in a true sense, we may say this thing. And this human civilization and material science, this human civilization and material science work on material science. They started together. That is the journey of material science and human on this earth are almost human civilization. Starting of human civilization on this earth are almost parallel and started together. Also, human civilizations are often divided into ages according to the materials that dominate in that society. For example, that Stone Age, that is lasted roughly 3.4 million years and ended between around 6000 BC and 2000 BC. And then Bronze Age, it existed between the 3300 BC to 1200 BC, and Bronze Age, it includes the copper and alloying it with tin and arsenic, and then also Iron Age and Steel Age. Actually, this Iron Age and Steel Age, this age is still continuing, but now in the last half we entered already the modern materials age, that is the plastic age. in the actually around 1925 or 35, this plastic age started, but it started in a full swing around in 1950 or 70, and that silicon age, it started around 1970 to 75, and it still now exists, and it's still now continuing in a full-fledged, that is the semiconducting age. But in the next or recent future, we may predict that we'll enter into the nanoparticles age and carbon nanotube age. And these new materials have fundamentally transformed our lifestyle forever and made a vast world into a global village. And the designed materials. The main interest of the material science is to prepare the design materials. And how these design materials can be made up? And these designed materials built up using the molecular building blocks at the molecular scale in predetermined manner. And therefore the molecules can be arranged in a particular way, changing their crystalline parameters, and this and thus a modified arrangement, molecular arrangement can be made. And this and also some other molecules can also be doped, and therefore the designed materials can be prepared. And these designed materials likely play a key role in the constructing and processing the future composite and integrated materials. And actually, in nature, there are several elements in the periodic table, as you know it from the periodic table, and also there are bioorganic molecules, namely, and these are naturally occurring bioorganic molecules, namely amino acids, nucleotides, lipid, etc. Also, numerous organic molecules. Some of the organic molecules are naturally occurring or nature-made. What we may say, it's a nature-made organic molecules. But along with this naturally occur organic molecules and bioorganic molecules or biomolecules, there are also numerous man-made derivatives. And every day, several man-made organic molecules and even biomolecules, they are added to the list. And these natural and synthetic building blocks, and these materials are designed artificially by human beings in their laboratory. And therefore, this subject also belongs to the material science. Some may say that these are the subject of organic chemistry. Some may say that these are the subject of inorganic chemistry, or some of the biological chemistry, some of the physics. But after all, these are all these subjects belong to a vast area of material science. And these natural and synthetic building blocks, much like the 26 English alphabet letters, and with the addition of foreign letters, are the key elements for the design materials. And foreign letters means when some other materials, some new materials can be doped. And therefore, these are the key elements for the designed materials. And also, another thing is that there are large number of scientists, they are working on various aspects of the material science, and this is evident from the publication of the papers. And with respect to scientific papers, this is the data of around 3 years ago. With respect to scientific papers, India ranked 6th with 12,693 papers, and India's research share all areas with respect to all the 3.88%. However, in case of material science, India's share with respect to world is 6.42%. And average impact factor for all subjects in all the branches, it is less than 1. But in material science, that average impact factor of papers is about 2 2.02 almost. This is the around 3 years later, before 3 years ago. And now, large number of institutes and universities in India also, various groups, and they are working on various aspects of material science. They may belong to chemistry, they may belong to physics, they may belong to any technological subjects, or they may belong to biology or any biological subjects, or even in material science subject. But after all, they are working in material science, and top 3 Indian institutes, research institutes, are Indian Institute of Science, Bangalore, Indian Institute of Technology, Kharagpur, Indian Institute of Technology, Delhi. Besides this, IIT Mumbai, and also TIFR, Tata Institute of Fundamental Research, and also in Kolkata there is also Cultivation of Science, Indian Association for the Cultivation of Science, also Jadavpur University, also Shah Institute of Nuclear Physics, and so on. Now we work on thin films, and this also falls under the branch of material science. And in our lab, we prepare thin films using some techniques, actually 5 standard techniques we use in our lab. That is, first is the most promising, that is the Langmuir project film deposition technique, LB technique, and then it is a layer by layer self-assembled technique, and then spin coating or spin casting technique, and then vacuum deposition technique, and self-standing method. Actually, this self-standing method has been introduced around 2 years ago, and it is also a very good method for preparation of somewhat rigid film. And for characterization, we use, for optical characterization or spectroscopic characterization, we use this UV absorption spectroscopy, fluorescence spectroscopy, FTIR spectroscopy, ATR FTIR spectroscopy, and for electrical spectroscopy we use 4 probe and 2 probe method, and for morphological spectroscopy characterization we use AFM, SAME, XRD, and also BAM, FIM. We use in situ BAM and FIM. In situ means these instruments are attached with the Langmuir project film deposition instruments, and we use these instruments to directly visualize the films during their formation. And these are the Brewster angle microscope and fluorescence imaging microscope. And materials we use, these are the organic materials, and also fluorescence dyes, and then polymeric materials, biomolecules, namely lipid, protein, enzyme, nanoclay platelets, nanoclay minerals, and also other nanoparticles. And mainly these nanoclay platelets and nanoparticles, we use charged anionic or cationic charged nanoclay platelets and charged nanoparticles for the preparation of the Langmuir project film and layer by layer self-assembled film. Now, what is a thin film? Actually, this thin film also belongs to these nanoparticles or organization of nanoparticles, and it is a 2D nanostructure. 2-dimensional nanostructure comes under the broad and hot topic, that is the nanotechnology. And few nanostructures are, that is the 2D structure, thin film of one layers or layers of same types of molecules, that is the monolayer film, bilayer film, trilayer film, and multilayer films of the prepared using the same types of molecules. And also the super lattice structures, that is the films when prepared by alternate deposition of 2 different types of molecules. And these are called the 2D structure because when we consider the thin films, its height is restricted. Actually, the height of the thin films is very, very small, of the order of nanometer dimension, and therefore the height is totally restricted or confined. and only we get the 2D structure, that is the length and breadth. And but there is also 1D structure, that is the 2 dimensions are confined, and these are the nanowatts, quantum watts, also nanorods, nanotubes, nanorods, carbon nanorods or carbon nanotubes. Also different nanowatts can also be prepared, and nano platelets. These are almost of 1D structure, because some of the nano platelets, they are of rod-like structures, and their dimensions are also very small. And 0D structure, that is the 3D confinement, that is the nanoparticles of the order of say 25 nanometer to 50 nanometer, and also quantum dots. Quantum dots also have dimensions of very small, less than the nanoparticles, about 1 to 2 nanometer their dimension. And they don't have any length, breadth or height. Only some very small dimension particles, their shape may be of spherical shape or some other shape like star-like shape or hexagonal shape or others, but their dimension is very small, of the order of 1 to 2 nanometer. These are called the quantum dots, and nanoparticles are of the order of say 25 to 50 nanometer or even say 10 nanometers also. And dimensionality and confinement depends on the structure. On the structure of the bulk, nanocrystalline films and nanocomposites. And using these nanoparticles, a nanocrystalline films can be prepared, and nanocrystalline thin films can be prepared where the nanoparticles are arranged in a particular manner. There may have some long range ordering of the nanoparticles in the thin films, that is some crystalline ordering may be observed in the thin films, and also in some other cases some short range ordering is observed, that is there is no long range ordering when the nanocrystals are arranged in the thin films. And this type of short range ordering, this may be, we may say that some aggregation or some amorphous types of organization of the nanoparticles in the thin films. Now, what is nanoscale? 1 nanometer is the 1 billionth of a meter, that is 10 to the power minus 9 meter. In a comparison, we may say that a girl is 4 feet height, that is around 1.219 meter, and that is 1.219 billion nanometers. And it is about 5 millimeters, that is 5 million nanometers. Actually, 1 millimeter means 1 million nanometers, that is 10 to the power 6, that is 10 to the power 6, 10 to the power minus 6 millimeters. That is 5 million nanometers. And similarly, human hair, the width of the human hair is very thin or very small width, not length. And that width is around 100 micrometer width. Wide on an average, this human hair, that is around 100,000. 1 micrometer means 1000 nanometer, and therefore 100 micrometer means 100,000 nanometer. And that human cell, it is around 10 micrometer, that is 0.1 millimeter, 0.01 millimeter. Its dimension is 10 micrometer about, that is 10,000 nanometers. And DNA is around 2.5 nanometers width, and the 10 hydrogen atoms, when they are placed side by side, when 10 hydrogen atoms are placed side by side, they give only, the length becomes only 1 nanometer. Therefore, you understand how small, how infinitesimally small a nanometer is. And also, in the present time, this nano or nanotechnology, this word is a buzz. Many people, they say this nanotechnology or nano, but certainly this nano car. This nano car is not an invention due to nanotechnology. A NASA definition, this is the nanotechnology is the creation and utilization of materials, devices and systems through the control of matter on the nanometer length scale. That is at the level of atoms, molecules and supramolecular structures. The term nanotechnology was invented by Taniguchi in 1974 and it was first popularized in 1980 by scientist and visionary K. Eric Drexler in his book The Engines of Creation. It is a very good book. I think that everybody should read this book. This book is available free of cost in the internet, and in this book a detailed discussion about how the nanomachines of the and nanomachines and molecular machines are created by nature, and even in our body, in any animal body, there are large number of these molecular machines like cell, and even within the cell there is mitochondria and others which are working as independent engines, and they produce, say mitochondria, they are producing energy, and they may be treated as molecular machines or nano machines, and they discuss in detail in this book, Engines of Creation. Now nanotechnology, actually this is the next generation technology where small is big, and not very fast, around 30 or 40 years ago when we have a big television set in a house, then we say that person is a very rich person. But nowadays, the TV is available on a small smartphone. And therefore, with the advancement of science and technology, we are going from big to small. And the small, when now, if we find that a person has a Apple smartphone, then we say that he is a quite rich person. And therefore, from the big to small, with the advancement of technology, we are going. And also that, but another thing is that Democritus in 400 BC, he said that to understand the very large, you must understand the very small. That is, to the molecular level and atomic level, we have to go. That is, to understand the very large, we must understand the very small. And there is plenty of room at the bottom. Was a lecture given by physicist Richard Feynman at an American Physical Society meeting at Caltech on December 29, 1959. Now, areas of applications of this nanotechnology has has found its vast applications in various fields, and with the passage of time, its application to various fields are increasing day by day. And this nanotechnology has application in the field of medication, in energy, even the solar energy cell, nano crystalline solar energy cells. These are also developed in the field of manufacturing, surgery, transportation, weapons, waste, textile, metals, organ growth, epitoxis, sensors, ceramics, electronics, plastic, disease treatment, also in the disease treatment. That is a large, vast work is now still now going on the drug delivery system using the nanoparticles as the nano capsule. Now, what is the so? Why the nanoparticles are so much important? There are various properties and various physical properties, chemical properties, they are vastly modified. When we go to the nano order dimension from the bulk state of say millimeter or centimeter or even meter dimension. When we go to the nanometer order, then the properties of the materials are changed fast. And these changes or changing in properties arises due to the one of the main important thing is the restriction of delocalization of free electrons. That is the extent of delocalization varies with the size of the system. When we consider say a metal of a bulk size, say around 1 centimeter metal dimension, or say around 10 centimeter dimension in metal, then the free electrons can move throughout the metal. But when you prepare a nanoparticles from this bulk metal, then the free electrons, the restriction is imposed on the free electrons to its free movement to all this 10 centimeter length, but they can move hardly within these nano order regions, and therefore a restriction of the movement of the free electrons has been imposed. Therefore, a restriction of delocalization has been imposed on the free electrons, and also, and therefore this restriction on the delocalization of free electrons, it gives rise to highly insulating nanoparticles that can be prepared using a highly conducting metals. Therefore, highly conducting metals, say from copper, copper nanoparticles can be prepared, and when these copper nanoparticles, all these copper nanoparticles are arranged to form a bulk nano nanomaterials of copper in the form of thin films, or simply as a bulk copper nanomaterials, and then this becomes the highly insulating nanoparticles. And also that structure changes with time. Also, that another thing is that optical properties also changes. The above two changes can lead to different physical and chemical properties depending on the size. For example, that optical properties also vastly modified when you go to the nano order dimension, because when light gets reflected from any substance, the size of the substance must be comparable with the wavelength of the light. But when you go to the nano order dimension, say around 20 or 50 or 100 nanometer, or say around 200 nanometer, prepare 200 nanometer dimension of the nanoparticles, and then the light which are scattered from these nanoparticles, their wavelength must be comparable, or at least to some extent may be greater, but not so much greater with the dimension of the nanoparticles. Therefore, when we go to different, when we prepare different dimension nanoparticles, say around 50 nanometer dimension, 100 nanometer dimension, or 200 nanometer dimension, and so on, these types of different dimensional nanoparticles, then their optical properties, that is their illuminating properties or light emitting properties, also changes. Therefore, the same materials, when we prepare the same nanoparticles using the same materials, therefore depending on the size, they may show different colors. Also, for semiconducting nanomaterials, their band gap is also highly modified, and suitable modification in the band gap can be made even by preparing different types of nanoparticles of different dimensions. Also, melting point also can be modified. High melting point can be achieved using, when you go to the nano order scale. The specific heat properties can also be modified, and then also that another important thing is the surface reactivity. When we go to the nano order scale, then their aspect ratio or surface to volume ratio, that is, for the same volume we get a large surface area, and this large surface area of the nanoparticles, it gives, it produces a high surface reactivity, because suppose when for any catalytic reaction, when you use any particle as a catalysis of a chemical reaction, and this, for the catalytic reaction, the reactant molecules needs to come in close proximity of the surface of the catalyst molecules. And when we go to when we prepare the nanoparticles of the catalyst, their surface area increases, and therefore their catalytic activity or surface reactivity or catalytic reactivity also increases to a larger extent. And also that another important thing is that this insulating property, when we go to the nano order scale, this nanoparticles, even the nanoparticles which are made up of highly conducting metals, but they may become highly insulating due to the restriction of the delocalization of free electrons. And even when such nanoparticles are consolidated into macroscopic scale, that is, using these nanoparticles when it prepare a bulk solid, or using these nanoparticles when it prepare a film, maybe thin film or maybe thick film, and then either bulk materials or in films, these new properties of the bulk materials of thin films are possible. Because these bulk materials or films, thick or thin films, they are prepared using the arrangement of the nanoparticles. But they are not prepared using the organization of the molecules, or to the organization of molecules or atoms at the molecular or atomic level. But they are organized, but they are prepared using the organization of the nanoparticles. Now, aspect ratio, we know that aspect ratio is the surface to volume ratio. That is for the same volume. That is for a sphere, it gives C by R. That is the for a sphere, if the radius is higher, then its aspect ratio becomes smaller. The smaller the radius, the higher the aspect ratio. That is, when you go to the small and small state, their aspect ratio also increases. We get an idea if we consider this picture. Here you consider the 1 centimeter cube. Say from a metal we consider 1 centimeter cube, and its volume is 1 centimeter cube, and there are 6 faces. Therefore, the total surface area becomes 1 centimeter square into 6, that is 6 centimeters square. Therefore, the aspect ratio becomes surface area by volume, that is 6 by 1, that is 6 per meter. But from this 1 centimeter cube, if we prepare a large number of only 1 millimeter cube, then we get 1001 millimeter cube. And total surface area of all these 1001 millimeter cube, it becomes 60 centimeters square. But the volume becomes same, volume becomes only 1 centimeter cube. Therefore, the aspect ratio becomes 60 per centimeter. And when you go to when we prepare the nanometer, 1 nanometer cube from this 1 centimeter, total 1 centimeter cube, when we prepare large number of 1 nanometer cube, then the total surface area becomes 6 into 10 to the power 7, 6 into 10 to the power 7 centimeter square. But the volume remains same, that is only 1 centimeter cube. And therefore the aspect ratio becomes 6 into 10 to the power 7 per centimeter. And hence it is observed that when we go to the nanometer scale, then their aspect ratio or surface area, surface to volume ratio or surface area increases to a larger extent in comparison to its volume. For example, when we consider a small drop of water, it may float. Say this drop of water may be of the dimension of say around 1 micrometer or say 100 nanometer, and then or 1000 nanometer, that is 1 micrometer. Then it can float in the air. But when it can float in the air because due to the high aspect ratio, that is its surface area is high in comparison to its volume. But when this 1 micrometer dimension, large number of 1 micrometer dimension water drops, they just coalesce or aggregate or merge to form a large water droplet. Then this water droplet falls on the earth's surface in the form of rain, and it cannot float in the air due to the less buoyancy or due to the less surface area, and therefore the buoyancy force is also less. It cannot float in the air, and it just drops on the earth's surface. Therefore, we see that this large surface area has vast importance to increase the buoyancy force also. Now, optical property, that is color change with size in nano dimension. Here, this is just an example that with the changes of the dimension and also changes in the shape, we get different color. These are the permanent colors. For example, this is the Ag nanoparticle, silver nanoparticles of the dimension of 100 nanometer. It gives around a red color, but this similarly this Ag sphere around 120 nanometer, it gives somewhat whitish color. And this Ag sphere around 80 nanometer, it gives some bluish color. Ag sphere around 40 nanometer, it gives some dark bluish color. And also that Ag prism, this shape is changed. This is around 100 nanometer dimension Ag prism, it gives a deep red color. And there are also different AU sphere. Ag sphere, this is AU sphere, gold sphere around 50 nanometer, this is gold sphere around 100 nanometer dimension. And with this optical properties, that is the color properties changes due to its dimension, because with the changing dimension, the light scattered of different wavelengths, they are also restricted, and therefore we get different colors from the nanoparticles, and these colors are permanent. These are the frozen colors, and these frozen colors are permanent. And using these properties of optical properties, it has different practical applications. Like nowadays, it has a vast application in the ornament industry, ornament preparation industry, and using these nanoparticles, permanent and very beautiful colors are important on necklace and also these bangles and even on the lockets. These are artificially, here the nanoparticles are imparted on these lockets or bangles to give a permanent color. These colors can never, using the same materials, different dimensional nanoparticles are prepared, and they are attached or imparted or tagged on these bangles or lockets to give a permanent, very beautiful color. And these are some examples of the naturally occurring nanoparticles. And the beautiful color of the wings of the butterflies, these are also due to the presence of nanolipids on the wings of the butterflies. Therefore, these are also the examples of the nanoparticles, naturally occurring nanoparticles or naturally occurring nanolipids. That another important property of this nanoparticles, some of the nanoparticles when some paints are prepared, and now these are industrially available, commercially available. Now these paints, when you paint your wall using this nanoparticle dispersed paint, then it becomes a dust-free coating on the wall, and whenever any dust, when you throw any dust on the wall, then this dust is totally repelled. Therefore, this wall always remains dust-free. And using these dust-free properties of this wall, even now industrially some garments are also produced, and where garments are painted with these nanoparticles, with these particular types of nanoparticles, which are totally dust-free garments, and no dust can be stuck on these garments. And therefore, these are the examples of the nano paint wall and nano cosmetics also. Other application of nanoparticles is the thermally insulating paints, and these paints are prepared by dispersing nanoparticles of highly insulating nanoparticles on a particular paint. And when some nanoparticles, I also discussed it previously, that suppose from a metal, when we prepare the nanoparticles, due to the confinement of the free electrons, these nanoparticles become highly insulating. And when these insulating nanoparticles are dispersed in a paint, and these paints are painted Using these paints, when walls are painted, then these walls become thermally highly insulating, 99.99% heat resistant. But it is not too much costly, but with the advancement of the technology, we will soon get quite cheap, in a cheaper rate, these types of thermally insulating paints. And thermally insulating gloves also available, and electrically insulating materials including gloves, and when some gloves are painted using these insulating nanomaterials, and then these gloves will also become thermally insulated, and also electrically insulated due to the confinement of the free electrons, and dust free paint for houses, cars, and others. And also that another important thing, or important application of the nanoparticle is now drug delivery system, and many researchers are now working on this drug delivery system, where nano capsules are prepared and suitable drugs or medicines are incorporated into this nano capsule, so that targeted drug delivery, so that when it is injected, then it go then these nanoparticles go to that particular infected area of the body and then burst, and then drug is released, and it has less harmful effect to the whole body. Now, recognition of nanoscience and nanostructure research, they received the Nobel Prize in 1996, that Carl and Mallet, and also Harold W. Proto, for the discovery of the fullerene 16, carbon 16. And it consists of carbon 6 molecules, that is, it consists of 60 carbon atoms bonded in a nearly spherical configuration due to the catenation property of the carbon atoms. And also its diameter is about 7 angstrom, 4.5 times larger as a hydrogen atom, or a bit less than a billionth of a meter. And Nobel Prize in 2007 was awarded for nanotechnology to Albert Ferd and Peter Grunberg. And another important thing is the further discovery of graphene. Graphene is a two-dimensional film of carbons, of the some allotropy of carbon, what we say, some hexagonal arrangement of the carbon atoms. And this Nobel Prize in 2010 was awarded to Andre Geim and Konstantin Novosel for the discovery of the graphene, for the groundbreaking experiments regarding the two-dimensional graphene material. And when these graphene materials are wrapped, it forms the carbon nanotube. The Nobel Prize in Chemistry in 2007, it was given to Gerhard Ertl, and this Nobel Prize in Chemistry in 2007 was awarded to Gerhard Ertl for his studies of chemical processes on solid surfaces, that is, on the thin films. An example of nanostructure is the carbon nanotube, and this carbon nanotube is 100 times stronger and 6 times lighter than steel, the strongest and the most flexible molecular material because of the carbon-carbon covalent bonding. Its Young modulus is 1 terapascal for the single wall nanotube and 1.25 terapascal for the multi-wall nanotube. But steel is only 230 gigapascal. That is 0.23 TP, that is terapascal, 0.23 TP. And the high aspect ratio, that is the ratio is about 1000 to 10,000, and density is also quite small. But electrical conductivity is 6 orders of magnitude higher than copper. Now, what is thin film? Is it a camera film? It is certainly not a camera film, but you consider the color in the wall. It's a coating of a film. It's a coating of a paint. Now, the coating of the iron rod or coating on the car window, these are all coating of a paint. And this coating, the thickness of this coating varies from, say, 100 micrometer dimension to several millimeter dimensions. And these are, to some extent, these coating cannot be said as the thin films, but they are called thick films to some extent, but not thin films. But these films can be used as a coating material, but for the thin films, their thickness varies from, say, 100 nanometer to 1 micrometer dimension maximum, or say around 10 to 25 or even 59 nanometer diameter. But for a monolayer thin film, its thickness may vary from say 1 to 5 nanometer thickness. And these thin films which are used in electronic industry are of nano to micrometer size. That is their thickness. And the special techniques are required to prepare such films. Even a thin film of only mono layer thickness, that is one layer or monomolecular layer of the film, can be prepared using some special techniques like Langur-Blodgett technique or layer by layer self-assembled technique. Now, why thin film? These nano to micrometer thick molecular films are found to be very promising in many practical and commercial applications. And the possible applications of these thin films, the possible applications include the fabrication of LED, light emitting diode, organic polymeric light emitting diode, and even inorganic light emitting diode also, a nanoparticle incorporated light emitting diode, and then electro and photochemical devices, electro-optical effects, possible structures for IC, and then novel materials for solar energy conversion, various templates to mimic biomineralization, switching networks using multi-layer LV film chips, optical switching and signal processing, nonlinear optical effects, single molecular memory chip, bio and optical sensor also. And these are some possible applications of the thin films in the electronic devices like in diodes, IC chips and others. The techniques for film deposition, and here in our lab we are working on the organic nanoparticles, polymeric materials and other biomolecules and also fluorescent molecules or laser dyes also. And these types of materials, thin film of this type of material can be deposited on a suitable solid substrate by various techniques. And these techniques include the spin coating, adsorption from solution, electro deposition, LB technique, Langur-Blodgett technique, layer by layer self-assembled technique, sputtering technique, thermal evaporation technique, and another most important thing is that lithographic technique. This lithographic technique has vast application in the IC fabrication industry. And here I will discuss this Langur-Blodgett film deposition technique and LBL, that is layer by layer self-assembled technique. And major groups in India, they are working, a large number of scientists from various research institutions and universities, they are working on various aspects of this thin film. And also throughout the world, from Japan, China, Taiwan, Singapore, and also Mexico, Singapore, UK, Brazil, USA, and also from large number of other countries also like Belgium, Sweden, Netherlands, Germany, Israel, and also some other countries also. A large number of groups, they are working on the various aspects of this thin film and using this Langur-Blodgett and LBL, that is layer by layer self-assembled techniques. And the research activities of this group related to LB and LVL films have focused on the following fields. Number one, in the fabrication of organic light emitting diode OLED and polymer dispersed light emitting diode. These are some vast commercial application also. In the fabrication of various sensing devices, namely gas sensors, biosensors, that is blood sugar sensor, alcohol sensor, etc. In the fabrication of solid state laser, in the molecular electronic devices, namely in the fabrication of FET, MOSFET, transistor, diodes, etc. In optoelectronic devices, in thin film solar cell, photodiode, etc. To work as model biological membrane to investigate the efficiency of various biological strainers. And there are also various other fields where LB and LB films have found their vast applications. We are also working on various sensors, application of sensors, and also in the fabrication of FET, MOSFET, and others. And also another important thing is that in laboratory, we are working to investigate the efficiency of various biological stainer using various biological dyes, biologically important fluorescent dyes. Now, Langmuir project film deposition technique. Some historical perspective of LV technique, oil film could be controlled by a movable barrier, and Agnes Prockel first observed this. And these films are of one molecular thick. It was concluded by Lord Rayleigh in 1899, and then Irving Langmuir. He just did some experiments and he showed that monolayer can be transferred from the air-water interface to the solid substrate. But that is, first of all, the monolayer is prepared on the water surface, and then this monolayer can be transferred onto a solid substrate from the air-water interface. And he also developed the theoretical concept and awarded Nobel Prize. And also there was Catherine Blozet. She first showed the possibility to deposit many monolayer onto the same substrate of required thickness, and thus multi-layered Langmuir-Blozet film where films were formed or were prepared. And now for the preparation of the Langmuir-Blozet film, the first important thing is the material chosen. The ideal material for the preparation of Langmuir-Blozet film is the amphiphilic molecules or surfactant molecules. And these amphiphilic molecules have two parts. That is, one is the hydrophobic part, other is the hydrophilic part. And this hydrophobic part, that is a long alkyl chain, which is a water heating part. And this must be large enough to make the molecule insoluble in the surface. And this is a long alkyl chain or some long phenyl chain. And they always tends opposite to the water surface. And there is another hydrophilic part, that is the water loving part. And they must have sufficient attraction to the water to keep the molecules anchored at the interface. And suppose this is the for an ideal amphiphilic molecule, this is the hydrophilic part, head part. We say it's the head part. It is the water loving part, and this is the alkyne chain part, long chain alkyl part, and it is a hydrophobic part or a water heating part. And when these molecules are spread on the water surface or at the air-water interface, then this hydrophobic chain, it tends opposite to the water surface. And this hydrophilic head group, it tends towards the water surface and then interacts with the water molecules, and as a result, almost the ideal amphiphilic molecules, they almost lie vertically on the water surface, but depending on some parameters like pH of the surface, concentration, temperatures and others, there may have some orientation or tilted organization of these amphiphilic molecules. And also when some other particles are incorporated, say some nanoparticles are incorporated between the space of the two amphiphilic molecules, then the parameters or their organizations may also change. As a result, some new vast properties are also observed. And this is the Langmuir-Blozet film deposition instrument in our laboratory. This is a Teflon made trough, Langmuir trough. It is made up of Teflon, and this is a process imaging microscope attached to the mini LV trough. And also here you look, this is the schematic representation of the Langmuir trough. It is made up of Teflon, that is the water does not wet this trough, and it is a barrier, computer controlled barrier. It is also made up of Teflon. And now when some molecules, some suitable amphiphilic or some other molecules, say non-amphiphilic also, or some polymeric materials also, or some nanoparticles also, and dilute solution, say in a volatile solvent, say chloroform. When a dilute solution of a suitable materials prepared in a chloroform solvent is spread gently on the water surface or at the air-water interface using a micro sealing by dropwise, and then sufficient time is allowed to evaporate the volatile solvent. Then the molecules, the amphiphilic molecules, they lie haphazardly on the water surface, as shown in this figure. And this state may be compared at the gaseous phase because the molecules are away from each other and there is less interaction between the molecules. But now, using a computer barrier control system, when the when this using this barrier, when these molecules are compressed slowly, then these molecules come closer and closer and they tend to orient in a particular direction. And after a certain time, it was observed that experimentally some measurement, actually from the isotherm measurement, it will be found that all these molecules are organized in a particular way, and thus a two-dimensional crystalline arrangement of the molecules will be observed. But further compression leads to the collapse of these molecules. And but before the collapsing, the two-dimensional organization of these molecules at the air-water interface, it states or it says the Langmuir monolayer at the air-water interface. And how the Langmuir monolayer, a stable Langmuir monolayer is formed at the air-water interface, it can be checked by the surface pressure versus area per molecule isotherm characteristic study. And it is observed that when the molecules are far away, initially the surface pressure becomes very, very small. But when the barrier is closed slowly and slowly, then at one point the surface pressure becomes steep enough. That is, surface pressure increases to a larger extent, but area does not increase too much. And this state, that is when a steep rise of surface pressure occurs, this region is called, then we may say that a two-dimensional crystalline arrangement of the molecules occurs. That is, a Langmuir monolayer is formed. But after further compression, there will be a collapse. That is, the pressure suddenly falls and collapsing of the monolayer will occur. And now, this Langmuir-Monod film deposition technique, and then after the Langmuir monolayer is formed, and this monolayer is formed, the orientation, organization of this monolayer, it depends on many other things, that is the pH of the surface, temperature, and also contact angle and others. And also, after the monolayer is formed, that monolayer is called Langmuir monolayer, and this Langmuir monolayer can be transferred onto solid substrate by the most convenient method is vertically depositing a solid substrate through the air-water interface. That is, we just take the solid substrate vertically into the water surface and then take it out. And by repeating this procedure, a multilayer Langmuir-Monod film, mono and multilayer Langmuir-Monod film can be prepared. And also there is another method which is called the Langmuir-Schaeffer method, and using this method, somewhat rigid Langmuir monolayer can be transferred. And here the substrate is used horizontally, is dipped horizontally, not vertically, and it touched the monolayer and then it just up, and such that the film is transferred onto the solid substrate. And this is called Langmuir-Schaeffer deposition technique, and it is used for somewhat rigid film, Langmuir monolayer, rigid Langmuir monolayer. And in this way, there are also other techniques like X-type deposition technique, Z-type deposition technique, and here the most convenient is the Y-type deposition technique. We also use that Y-type deposition technique. And here you look, the same types of molecules are used for the deposition of multilayer in Y-type deposition technique, in X-type and Z-type also. And superlative structure, when two different types of molecules are used for the preparation of two consecutive layers. This is the first layer here, and the second layer, in the second layer some different other molecule is used. Therefore, different molecules are deposited in alternate layers, and thus a superlative structure is formed. And if this is animation of the Langmuir-Molauget protein Langmuir-Molauget deposition instrument. And this is a Langmuir trough, and when some drops of dilute solution of a suitable molecules are sprayed, then solvents are evaporated and the molecules lie haphazardly on the water surface, and then barrier is compressed slowly. With the compression of the barrier, molecules come closer and closer, and this isotherm curve shows the surface pressure increases. And when the surface pressure attains the almost deep region, we get an crystalline arrangement of the molecules in the two-dimensional surface. And then the then the substrate, solid substrate, can be can be taken out from the within the water surface, so that a monolayer is deposited on the solid substrate. And during the preparation of this Langmuir monolayer and Langmuir film, and actually during the preparation of the Langmuir monolayer, some special techniques or characterization techniques are used to observe the formation of this Langmuir monolayer. This is the surface pressure versus time at constant area. This is called the adsorption kinetics, and area versus time at constant surface pressure, that is the stability. Once the Langmuir monolayer is formed, stability needs to be checked, and then surface pressure versus area at constant temperature. This is called the compression isotherm, and this is the most important thing that we have to check to get an idea about the preparation of the two-dimensional crystalline films, Langmuir monolayer. And then monolayer transfer onto solid substrate, glass or quartz substrate, and then characterization by FECM, TEM, fluorescence spectroscopy, and other characterization techniques. Now, importance of LV film studies: it is a unique blend of physics, chemistry, and molecular engineering, and understanding of structure property relation, and homogeneous deposition of the monolayer over large areas, multi-layer structures with varying layer composition, assembly of individual molecules into 2D and 3D systems, and control of film structure and monolayer thickness at the molecular level. And almost any kind of solid substrate can be used for the preparation of Langmuir film. And LV film on solid substrate, these are the superlative structure to different types of molecules, and these are the multi-layer film structure. And using Langmuir film, some different types of technological applications, and also for CD coating material, it has found some application. And for some diode materials, when we prepare using an N-type material, first coating, and then for P-type material, the first coating, then large number of diodes can be prepared on a single substrate, and it is possible to accommodate 10,000 such molecular diodes within 1 millimeter. And also this MOSFET structure, this is also can be prepared using this LV technique. And another important application of this LV and LVL technique, the film deposition technique, is the preparation of the light emitting diode, and some suitable fluorescent dye or some suitable fluorescent organic molecules. They are coated on the thin films using LV or LVL technique. Somewhat 20, 30 or 50 layers are deposited on a transparent anode, that is ITO, indium tin oxide coated glass substrate, and then a metal cathode is deposited over the layer, fluorescent layer, and then when it is biased, then light is emitted from these dye molecules or this dye layer. And this is the simple fabrication technique of the organic light emitting diode, or polymeric dispersed or nanoparticle dispersed light emitting diode. Also that sensor, that blood sugar sensor, and this small strip, many of you may see it, it's a small film. A suitable molecules is coated, biomolecule is coated on the solid substrate. When you, and initially its conductivity is low, but when you put a drop of blood on this film, its conductivity increases due to some chemical interaction. And this increase in conductivity, its current increases, and this current is calibrated to the sugar, blood sugar, and thus you get an idea about your blood sugar. And thin film transistor, that is the TFT monitor, can also be used, can also be prepared using this technique. And display, that another important application of this OLED is the display, flexible display. And this flexible display, in near future, this type of flexible display will come when suppose it will be in the form of a calendar. You just hang it on your wall and apply a small voltage, small power, say around 5 or 10 watt, the whole room will be illuminated. And in recent time, various non-amphiphilic materials and also water-soluble ionic dyes and nanomaterials are being used to fabricate Langur-Blodgett films. In case of ionic water-soluble molecules, first of all, a suitably oppositely charged template Langur monolayer is formed at the air-water interface, and then the ionic water-soluble molecules are allowed to be adsorbed from the aqueous surface into the preformed ionic monolayer at the air-water interface. Thus, a complex monolayer is formed. When inorganic nanoparticles are allowed to be adsorbed into the preformed monolayer, then hybrid Langur monolayer is formed. A layer by layer self-assembled technique, this is also a quite easier technique using this deep automatic control deep coater unit. It is possible that first of all a positively charged, the solid substance is dipped into a positively charged solution of a positively charged polymer or other materials, then it is washed in a pure water, deionized water, rinsed. So to wash off the excess positively charged particles, and then again it is dipped into the negatively charged material solution of the material, and then again it is taken and washed into the water. Thus, a bilayer coating of positive charge and polyion, anionic and cationic materials, bilayer of anionic and cationic materials is prepared. Thus, an LBL film is formed, and it can be controlled automatically, prepared automatically using this deep coating instrument. Now, our work on LB and LBL thin films. Preparation of two-dimensional ordered films of organic, polymeric and organoclay hybrid films. Here we use using this Langur-Blodgett technique and layer by layer self-assembled technique. Study of organization of clay particles and adsorbed molecules, nanoclay particles and other nanoparticles and adsorbed molecules, and controlling of different types of aggregates in the ultra thin films. And also we work on fluorescence resonance energy transfer. And our goal is to explore new nanomaterials with different functionalities for their applications in sensing, biosensing, catalysis, optics, electronics, etc. And to study the fundamental properties of single clay mineral particles, to study the organization of clay particles and adsorbed molecules, organization of clay sheets onto thin films, nano clay sheets onto thin films, and that of organic molecules onto clay surface. And how this clay dispersed film is formed. And here to look, this clay dispersion is prepared using milk poured water and stirred for 24 hours using the magnetic stirrer. And clay dispersion is ultrasonicated for 30 minutes before use. LB trough is filled up with dilute clay dispersion consisting of single clay sheets. Chloroform solution of amphiphilic cation was spread onto the surface. And when this clay dispersion water surface is filled up in the LB trough, and then preformed oppositely charged, the cationic charged amphiphilic molecule, and their monolayer is prepared. And then due to electrostatic interaction, these clay particles, nano clay particles, are adsorbed onto this preformed monolayer, and thus a hybrid monolayer is formed. Clay dispersed or clay tagged hybrid monolayer is formed, and then using the conventional technique, this can be transferred onto solid substrate to prepare mono and multi-layered hybrid films. And these are some AFM images of the organoclay hybrid monolayer. Here it is the rod-like hectorite structure, and these are the some laponite, some plate-like, small plate-like, around 25 nanometer dimension, laponite, AFM images, the laponite deposited onto LB film. And two-level organizations exist in this organoclay hybrid film, and these are the solid substrate, and on the solid substrate, these clay layers are tacked, and on these clay layers, these organic molecules are tacked. But some of the organic molecules may also tack on the solid surface substrate separately, and therefore, in this way, the organoclay hybrid films are prepared. And that another technique is the Brewster angle microscope. Using this Brewster angle microscope in situ, this is the LB trap, and these are the Brewster angle microscope. Using this Brewster angle microscope, a film at the air-out Langmuir monolayer at the air-outer interface can be directly visualized during its formation. And here you look during the formation of a Langmuir monolayer at the air-outer interface, using these are the Brewster images, or BAM in Brewster angle microscopic images, or BAM images. Here, initially, it was observed that these are the black voids. That is, here there is no absence of the material. Only these white illuminated regions, there are materials. And when the surface pressure increases, and then the voids, number of voids and their dimension decreases, and at the large surface area, a white illuminated region is formed. That is, a total uniform film Langmuir monolayer is prepared. Another important thing is that initially it was observed that when we use some other materials, then initially these materials are separated well enough. But with the passage of time, there are some interaction. But with the passage of time, when some nanoparticles, these are the nanoparticles BAM images, and when the nanoparticles are incorporated, then some highly long range ordering of the crystals is formed. And when the surface pressure attains a plateau region, then a long range ordering of the crystal and crystal in two-dimensional Langmuir monolayer is formed. And that another thing is this micelle. The Langmuir monolayer of the nano micelle capsules can also be prepared and can be visualized using the BAM images. These micelles and vesicles nano capsule. And when these micelles or vesicles, some fluorescent dyes are tacked into the micelles or vesicles, then initially before the starting of the interaction, small domains of the micelles, micelles are observed, and with the passage of time, the nanocapsules are incorporated, fluorescent dyes are incorporated into these nanocapsules, and their dimension also increases. And after the completion of the reaction, large domains of these fluorescent molecules incorporated micelles are formed, and a almost uniform film structure is observed. And also this RAM and worm, we are also working, and different sensors developed in our lab in the recent past, that is arsenic sensor, hard water sensor, pH sensor, ion sensor, DNA sensor, cholesterol sensor also. And that another important findings, the colorimetric sensor in our lab we worked on. And initially this nanoparticles incorporated Langmuir film of 20 layer is deposited. It almost bluish. But this is a film, just freshly films after 5 days without alcohol. And then in the B, the film after 5 times puff, after 1 hour of consumption of 2 peg alcohol, puff by a person who just consume 2 pegs alcohol and after 1 hour, and then it gives a crimson red color. But film after this C, it shows the C film after 5 times puff after 4 hours of consumption of 2 peg of alcohol, and it gives somewhat faded color, but still there are distinction of the color with the freshly prepared, that is without interaction with any kind of alcohol. There is this. Therefore, just by using a strip, this can be used commercially quite easily using a strip, and when any person just puff, its color changes. Just by observing the changes in color, where it can be concluded whether a person consumed alcohol or not. And these are some instruments, that is fluorescence imaging microscope, Langmuir project film deposition instrument, automatic computer control, programmable spin coating, vacuum deposition unit, self-turning unit for film preparation instruments, and these are the instruments for characterization instruments. AFM, process spectrophotometer, process picosecond, lifetime spectrophotometer, UV subjection, FTIR, millipore, Keithley source meter, and others also. And these are some of the instruments available in our lab. Langmuir project: film deposition instrument, deep coating unit, spin coating unit for and vacuum deposition unit, and characterization UV subjection, process spectrophotometer, and then FTIR, ATR, FTIR spectrophotometer, process lifetime, atomic AFM, in situ imaging, FIM, process imaging microscope, in situ Richter angle microscope. It was installed around 2 years ago. And for electrical characterization instruments and major projects are these are. I also got some, and Asad, he also got some of the projects. And thank you all. This is the end of my lecture.